Logic gates and Boolean expressions. In this presentation, we're going to be looking at Boolean expressions, some little bit of Boolean algebra, and one of the fundamentals, which is demorganizing. Well, let's get going. Boolean expressions. Now, Boolean expressions are used to describe a logic circuit without sketching the logic symbols. This is called an expression. Each letter in the equation represents an individual input or output on the logic gate. And, well, honestly, it looks like a mathematical expression. So let's take a look at a NOT gate. A NOT gate has an inverting circle on the output side, and this is usually the only one that has the same letter used for the input as it does for the output. Now what we'll notice is that there is a horizontal line drawn above the A. The line over the top of a letter means it's inverted, or opposite, and we know that to mean that if the input is high, the output would be low. So it correlates to this dot. An AND gate has a dot in between the two inputs. Now this could be a 2 input, a 3 input, or a 4 input. There would be a dot in between each, or sometimes there will be no dot at all, and the A and the B will be right beside each other, sort of reminiscent of multiplication in mathematics. So the dot means that both the inputs must be high for the output to be high. When we see this Boolean expression, what needs to come to our mind is the shape of an AND gate. Now, new logic gates can be created by combining NOT gates on either the inputs or the outputs, or sometimes both, of an AND gate. So this is how we get NAND and negative AND. A NAND gate is with one NOT gate on the output of an AND. And a negative AND is with two NOT gates in series with each of the inputs to the AND gate. If we were to take a look at the Boolean expression for all three of these, we would then see the AND gate has a dot in between, standard AND. A NAND gate has the inverting output and a line over top of the A and the B. And then the negative AND has two dots here, meaning inversion, and that means that the A and the B have separate lines over top of one another. And that's an important difference to keep in mind. They represent two different logic gates. So again, if the output is inverted, a single line or bar is drawn over all of the inputs of the logic gate. Whereas if there are two separate input NOT gates, then you have an input bar drawn over each one of the input letters. If we look at the OR gate, the same thing can take place. We can, in an OR gate, add additional NOT gates to either the inputs or the outputs. So let's just first start with the OR gate. An OR gate, as a Boolean expression, is a plus symbol in between the A and the B. So two inputs with a plus symbol between them mean that either input can be high for the output to be high. So that would be an OR gate. As we said before, you can build new logic gates by adding NOT gates into strategic locations. By placing a NOT gate on the output of an OR gate, you get a NOR, whereas adding two NOT gates on the input of an OR gate, we get a negative OR. In the same way, we can then show the Boolean expression having the A plus the B, but when we have the NOR gate, we have a single line that goes over top of all of the inputs, and when we have a negative OR, we have individual lines that go over each individual input. Now, many individuals find the below combined logic gates confusing to interpret. What often helps is to break the logic symbol down into its most basic form. So these are examples of NOR, NAND, negative OR, negative and well, some really weird ones at the bottom here where we've got NOT all over the place. And so people often bang their head against the wall thinking, how on earth, I can't figure this out. What's in, what's out, what's high, what's low? And for the purposes of the average electrician, I would say the easiest way to go about interpreting this is to break it down. And what I mean by that is actually sketch the NOT gates. So let's take a look at each one individually. This one up here is really, we've got an AND gate, and a NOT gate. Now I understand how an AND gate works, and I understand how a NOT gate works. If I put some separation between the two of them and treat it as two separate logic gates, it becomes much easier for me to determine what the output should be on the far right-hand side of this logic gate, simply by breaking it down. So the output for this one would be low. What about the next one down? Well, the next one down is really an OR gate with a NOT gate. So if I have a OR gate here, and that's low, then that means the output is low. Well, if it's low going into the input of a NOT gate, that means the output must be high. And that then means that for this logic gate, the output will be high. What about the one below? This would be a negative OR gate. Well, it's simply just two NOT gates, and each is wired in series with the input. So we can see here, coming into the NOT gate is a high, which means a low on the output. On this one is a low, meaning there's a high on the output of the NOT gate. This is an OR gate, which means either one going high will elicit a high on the output. So there's my high, and that means that this logic gate would have a high output. Now for the next two following, we'll go through them a little bit quicker, but really it's just the same process. Sketch it out. Don't draw out the agony of trying to figure these out. Just sketch it. Sketching it makes it easy. So here's a whole bunch of NOT gates. There we go. Two highs means two lows. And this is an AND gate, which means, well, two lows mean a low. And if there's a low, that means there's a high on the output of the NOT gate. And, well, that means there's a high coming out of this AND gate. And finally, the last one, oh, lots of weird stuff going on there, right? A high and a low. So high into the NOT means a low coming out. And this one means a high coming out. This is an OR gate, which means the output should be high, which we see here, going into the input of the NOT gate, which means the output of the NOT should be low. And that then results in a low output. So a handy little trick. Now, Boolean algebra is mathematics, and it's used to analyze digital gates and circuits. And we use these laws of Boolean to both reduce and simplify a complex Boolean expression in an attempt to reduce the number of logic gates required. Now, Boolean algebra is therefore a system of mathematics based on logic that has its own set of rules or laws which are used to define and reduce Boolean expressions. There are 12 of them. Think of these as rules or laws that you would use in the same way in mathematics when you were trying to reduce an algebraic equation. If you were trying to simplify one, you would find things that could be crossed off or canceled. Now, for the purposes of this video, I'm not going to be going through all of them. To be quite honest, I don't think it's a skill that most electricians require. We are going to focus on one, De Morgan's law, but before we get to that, I'm going to show you how each of these laws, what the rationale or the final sort of solution may look like for a complex logic gate system. So let's start with this. This is a 3-input, it looks like 4, 5, 6, 7 logic gate circuit with one output. So what we're going to do is we're going to put each of the expressions for each one of the logic gates, and then through the magic of all of my distribution laws, we are then going to work out what the simplified Boolean expression would be. But I'm not going to go through each step. So the first one is an AND gate, and it looks like we've got here A and M. So it's an AND gate, means we got a dot in between. This is another AND gate, and it looks like we've got still two inputs, M and C. Then we got another AND gate, 2 inputs. This one looks like they are A and C. And then finally, the last one is 3 inputs. That's A, M, and C. All right, so that's pretty simple. Let's take a look at these ones up here now. So this one is an OR gate, and it's a combination of M, which is all the way over here, and the output of this AND gate. And so we're going to have to work out what that expression would look like. And just like in mathematics, you'll often see brackets. So M plus MC. The plus is representing the OR gate, which is this. It's either this, M, that would be this signal coming in, or It's whatever comes out of the AND gate. And what comes out of the AND gate is based on M and C. What about the next OR gate? Well, this one's based on 3 different inputs. And these 3 different inputs are coming from 3 different AND gates. And so each of these are going to have to be combined with a plus symbol in between them. And we're going to have to use some brackets to keep them separate. So we got AM plus AC plus AMC. And that's just each of these. All right, well, the last one is then this. And as you guessed it, we're going to have to take into account the 2 OR gates that are supplying the input to this final OR gate. So we're going to have this, and we're going to have this. So we're going to start with the top one, M plus MC. Notice how I got brackets in there. Plus, then I'm going to have the bottom string down here. There we go. Now this is really as far or as deep as I'm going to take it. I'm not actually going to show you how to apply all of these to simplify the Boolean algebra. All I'm going to show you is the product that we get after. So if you go through the process of simplifying a Boolean expression with these Boolean algebra laws, you would come out with this. X, the output, is equal to M plus AC. Vastly simplified. And what that means, the significance of it, is that you could build a vastly simplified logic circuit that would operate exactly the same as this 7 logic gate monstrosity. 3 inputs, 1 output. This is the same as this. The more basic you can make your controls, the easier it is to troubleshoot and the cheaper it is to produce. So this would be the exact same operation of circuit. 1 OR gate, 1 AND gate. Interesting, hey? Now the only Boolean law that we really want to look at is called De Morgan's law. And that's what I said earlier. And De Morgan's law says that this logic gate is equivalent in operation to this logic gate. Well, that's just crazy. Now, De Morgan's law is pretty darn simple. It's based on 2 rules. The rules are start with a logic gate, and if you want to find the De Morgan equivalent, you are going to choose the opposite logic symbol. Now, don't worry, there's only 2 to choose from. There's AND gates and there's OR gates. So if you start with an AND gate, you're going to sketch an OR gate. The second step is to negate all inputs and outputs. So that means if the output was already negated, you're going to negate it, which means, well, it's no longer negated. Another way to put this more plainly is to put a circle where there was not one before and remove a circle where there was one. So pretty simple. And what you'll notice if you do the truth tables for each of these, they operate exactly the same. 2 highs coming in on this AND gate will make a low on the Y. And that will be exactly the same on this one. So we would have this. A dot B, a line over both. And then here's the Boolean expression A with a line plus B with a line. Now here's a different example. This is a NOR gate. Now what's the De Morgan equivalent? Well, I'm going to have to sketch an AND gate first. And then I'm going to have to negate or sketch circles where there were none before and remove the circle where there is one presently. So that gives me a negative AND. I've got an AND gate. There is no negation on the output, but there is negation on each of the inputs. And again, we have A plus B over here with the line over both, and A dot B with individual negation lines over each of the inputs. Now, some might ask, why demorganize? Well, simply another way to represent the same logical operation, and if applying many algebraic laws, a demorganized symbol may make for an easier simplification. So sometimes it becomes easier to simplify if I demorganize something. So here are some more demorganized logic gates. So a little bit on Boolean expressions, a little bit on Boolean algebra, and a little bit on demorganization.